Hey everybody, I'm Dennis and I'm going to talk about the HICANN wafer system, which is one of the neuromorphic hardware systems developed in Heidelberg. So let me start. Let me introduce you to HICANN, the high input count analog neural network chip. So HICANN is built of lots of electrical stuff, synapses, memory, and 512 analog neurons. So what does that mean that the neurons are analog? That means you do not solve a differential equation numerically on your conventional computer, but instead you have a physical representation of that differential equation in silicon. That means you have an analog electrical circuit that behaves like a differential equation. For example, you have a capacitor that is the physical representation of your membrane potential, just as an example. So analog neurons have some implications. First of all, you have only one neuron model. If you want to have another neuron model, you've got to build a new chip. Then you have variations. If you do the same experiment twice, you will never have the exact same results. And since electrical parts are not identical either, you also have variation across neurons. And these are things that have to be handled. One thing we see else in the name is that you have a high neuron input count at the HICANN. That means you can have more than 10,000 synaptic inputs to one neuron. So that's why the area for the synapses is actually so great compared to those few neurons here. Okay, now we have 512 neurons on this HICANN. Well, 512 neurons you can simulate mostly on your conventional computer. That's why there are 384 of these HICANN chips on this little wafer down here. So that means you have on one of those wafer modules up to 200,000 neurons and 40 million synapses. But since more is always more, we put 20 of those into one of those racks, and that's what's happening right now in Heidelberg. So you end up with a system of 4 million neurons and towards 1 billion synapses. So there's a nice side effect of these analog neurons is the electrical parts are really small. So that means the time constants are also really small, and that means everything is happening really fast. So you have an acceleration of up to 10,000, a factor of 10,000. That means if you want to simulate 10,000 milliseconds in biological real time, it takes only 1 millisecond on your hardware. So this is one of the promising parts of this hardware, that you can actually do long-term investigations of networks. Yeah. Okay, let's take a look at some emulation experiments that can be done on the HICANN already. So these are demonstration experiments to show that the functionality you want is you can find on the networks like this. So this is just a very simple feed-forward network. You have a spike source that's stimulating one population, and every population is connected, exciting the next population, and you can observe that the activity is propagated through the populations and have similar results in simulation and emulation on hardware. Another network that I investigated in my bachelor thesis is just a very simple recurrent network. You have two populations, both inhibit each other, both are excited by two different sources, and you can observe some competitive dynamics. And then we heard about that today, the closed loop experiments, like if you have a robot where you can kind of connect some neuromorphic hardware in your system. So this is, for example, very simple simulation. You think of a dot, one-dimensional environment, virtual environment, it's just moving, and you have velocity and a position, and that's happening on software up here, velocity and position, and that environment determines some input to your neuromorphic hardware, neural network, that somehow calculates some action, for example, move your head to the dot, and that again changes the virtual environment. And that's also possible to do on this hardware. So time is done, yeah, done.
Is there anything you want to highlight there?
Yeah, it is. So the extra experimental challenge is that you minimize the variations. And that's done by calibration and increasing population sizes so that mean behavior is predictable. And one of the major outlooks is that you can actually do experiments on large time scales. So you can investigate, for example, long-term learning behavior or do structured plasticity learning. Yeah, thank you.